Welcome back, class. So today I want to wrap up Chapter 10 by talking a little bit about ionic bonding, and not so much how Lewis structure does it, but just in general how we think about ionic bonding and how it can be used to make predictions, and a little more in detail about what we think about when we think about ionic bonding. And then at the end, we'll very briefly mention a little bit about metallic bonding. So first of all, let's just talk about some of the things that we think about ionic bonding. So if we think about Lewis theory and the idea that metal atoms will lose electrons and non-metal atoms will gain electrons in order to obtain a stable, noble gas octet environment, right? So that's the idea. So this allows us to do what we've already learned how to do, which is predict ionic compounds from formulas, right? Or predict the formulas of ionic compounds, right? Because we know that an ionic compound has to be neutral. So if we know what the charges are in the metal and the charge in the non-metal, we can predict what the ratio of metal to non-metal so that we end up with a neutral compound. And this can tell us what the ratio of positive ions and negative ions is going to be in our crystal structure, in our lattice. Now, another idea is that the electrostatic attraction between the ions, so the positive attracting the negative, is considered non-directional in an ionic bond. So, in other words, the ion puts out its positive charge or negative charge in all directions, and so there is no direct pairing, if you will, right? It's not, in the structure, it's not like there's this ion paired with this cation, right? We have a structure in which we have alternating positive and negative ions in the ratio to give us an overall neutral structure. And so, of course, in an ionic compound, we have no molecules, right? We think of things as a crystal lattice, and the formula that we use, such as sodium chloride, right, for example, is an empirical formula that gives us the simplest ratio of the positive and negative ions, or the metal and the non-metal ions, in our structure. This can allow us to predict relative strengths of bonds using something close to what we think about as Coulomb's law, and we'll talk a little bit about that. So, our lattice. So we talk about these crystal lattice, but we haven't really talked much about the energetics of the crystal lattice. So we know that when we break down the lattice, right, it's going to take energy, right? So it takes energy to break down this crystal lattice. Now, what we haven't really thought about probably is if it takes energy to break the crystal lattice, then energy must be given off when the crystal lattice forms. Right, so if we think about this picture, and we think about all of our ions coming together, now ideally in the gaseous state, right, to come together to form the sodium chloride crystal, that process is very exothermic, right? It's going to give off a lot of energy because, as we talked about with covalent bonds, right, when we make a bond, it's exothermic, right? We give off energy in the formation of the bond because we're going into a lower energy state. And so that extra energy is released. Now, in ionic bonding, we call that the lattice energy, right? So this is the energy released when the solid crystal forms from the separate ions, ideally in the gaseous stage, right? So I talked about it's exothermic, but of course it's hard to measure directly, right? This is not something that we can model easily or do experiments, right? So typically what we do is we do like a Hess's law approach, right? Where we look at all the processes that are involved in getting from the elements into the final crystal lattice, and we look at all the processes we can get, and then we solve for the lattice energy based on knowing everything else. Now, lattice energy, what does it depend on? So we're going to talk about a couple of these, but briefly it depends on the size of the charge and the distance between the ions. right? So those are going to be the variables that affect the value of the lattice energy. Now, we use what's called a Born-Haber cycle to a hypothetical approach to looking at the process going from individual elements into crystal lattice. So it's what we call a hypothetical series of reactions. Now, what we mean by that is that these are real reactions, meaning they could actually happen, but we don't necessarily think that the crystal structure actually forms by going through this stepwise process. But we can simulate it in this way. Now, we choose the reactions so that the overall process, which is going to be the enthalpy change, right, of the reaction, right, of the overall crystallized, and every other value is known except for the lattice energy. And then we use a Hess's law approach, right, which means we can sum up individual reactions, add up the enthalpies, and we get the overall enthalpy for the process. So let's take a hypothetical reaction here. So if I want to look at the delta H of reaction for the formation of an ionic compound, or what we call a salt, we could think about all of these steps being involved. So first of all, we have a delta H to form metal atoms, right, into a gas. So in other words, we have to vaporize the solid metal. We have the energy involved in turning the non-metal atoms into a gas. So we have to vaporize the non-metal. We have the energy involved in forming the metal cations, right? Remember, this is going to be of ionization energy. Now, depending on the charge, there may be multiple. So if we're forming a positive 1, then it's just going to be the first ionization energy. If we form a positive 2, right, then we have a first ionization and a second. So we have as many ionizations as we need based on the positive charge. Now, we also have the energy involved in forming the negative ion. This can be looked at in terms of the electron affinity, right? That's a value that can give us the energy involved in forming negative ions. And then finally, we have the energy involved in taking those separate gaseous ions and putting them together into the crystal. This is our lattice energy. Right here. So let's think about this. So we're going to find a value for this number, this number, this number, and this number, and we're going to know the overall process. So our variable, our missing value, is going to be the crystal lattice. So this is the approach we're going to use. So we can diagram this. So let's zoom in here just a little bit. And we can sort of think about these steps. So if we start with sodium and chlorine. Now, first of all, we're going to vaporize the sodium, right? And this is going to take energy, right? This is going to be an endothermic process. So we have to go from solid sodium to gaseous sodium. Now, chlorine is already a gas, but we do have a process here, and that is because chlorine exists as Cl2, we have to break it apart into individual chlorine atoms, so Cl atoms. So there's an energy associated with forming chlorine atoms from the chlorine molecule. That's, again, also going to be endothermic. And then finally, we have the value of taking sodium gas and chlorine gas and ionizing them. Okay? So first of all, we'll ionize the sodium. So we'll form positive ions, right? This is going to be an endothermic process. So it's going to take energy to pull that electron away. Right? So we have 3 endothermic processes, right? The formation of gaseous sodium from solid sodium, the breaking of the chlorine-chlorine bond, and the formation of the positive ion, the ionization energy, right? Ionization energies are always endothermic because they involve pulling something away. what other steps do we have? Well, we still have to make the chlorine ions. So we have to form negative chlorine ions. Well, this is going to be an exothermic process because we're creating an interaction. We're adding an electron to form that chlorine negative charge. So that's going to be an electron affinity, which is going to be an exothermic value. And then finally, we have the crystal lattice, or the lattice energy for the formation of sodium chloride, right? And that's here. And as you can see, this is by far the biggest energy. And again, it's always going to be exothermic. And the difference between the energy we put in, right? So we have the energy input, this is what it cost, and the energy output, right? This is what we get back. So that difference here is the enthalpy for the formation of the reaction, right? So this is the delta H value. Now, the idea is we're going to know everything except our our lattice energy. So now we can sort of see it diagrammed. Let's look at numbers. Okay, now of course, these numbers are going to be provided for you, or you're going to be able to find some place where you look them up. So let's just look at these. So to go from solid sodium to gaseous sodium, that's an enthalpy of sublimation, right? So we're going from a solid to a gas. And the value for sodium is positive 108 kilojoules. So again, an endothermic value. We have to break a Cl-Cl bond. So that's the bond energy of a chlorine-chlorine single bond. And that's 244 kilojoules. Now, we multiply it by a half because remember in our balanced equation, we just have half a mole of Cl2. Now, we have to take sodium into sodium ions. Again, that's an ionization energy. That has a value of 496 kilojoules. Is the first ionization energy for sodium. Then we have the electron affinity to create the chlorine ions. Again, that's going to be a negative. That's an exothermic process, an electroaffinity. The lattice energy, of course, is unknown. This is our unknown value. And the overall delta H of formation for the formation of sodium chloride is a negative 411. So this is our sum, and the process is made up of these 1, 2, 3, 4, 5 processes, and we know 4 out of the 5. So we have one unknown, and that is the lattice energy. So if we sort of lay this out, and we have the delta H of formation, so this is my negative 411, equals the delta H of sublimation for sodium atoms here, the breaking of the chlorine-chlorine bond here, the first ionization energy of sodium here, the electron affinity of chlorine here, and then of course the lattice energy. So we want to solve for this, so we want to move everything else to the left side of the equation. So we get to the lattice energy is going to equal our delta H, right? That's the negative 411. And we're going to subtract all of those other things from both sides of the equation. So we're going to move it over, so it's going to be minus the sublimation energy. Again, half of the bond energy, the first ionization energy of sodium, the electron affinity of Cl. So if we do all that math, we get an overall lattice energy value of negative 788 kilojoules. And again, it should always be exothermic, and they're going to be big, right? Notice on that chart, right? It was by far the biggest. If you look at comparatively, right, this is much bigger than any of the other individual values. So that's how we can go through a Born-Haber cycle using kind of a Hess's law approach to solve for the lattice energy. And so some commonalities, right? These lattice energies, again, will always be exothermic, and they'll always be quite large. Okay, so let's talk about some variations in lattice energy, meaning how can we predict whether something's going to have less or more or less, a higher or lower ionization energy to lattice energy to something else. So first of all, the attraction between the charged particles is inversely proportional to how far they are apart, meaning the closer they are, the harder it is to separate them, right? So if they're closer together, there's going to be a stronger bond. It's going to be harder to break. If they're farther apart, that's going to be a weaker bond. It's going to be easier to break, less energy. So one of the things that has an effect on bond length, right, is the size of the atom. So remember when we looked at bond length and bond strength, if you will, right, that if we looked at a series of bonds to the same atom with progressively larger, like the halogens, right, we saw a lowering of bond strength as the bond length got longer, right, as we went to bigger atoms. So we can look at that in terms of lattice energy, right? So if we look at the salts or the ionic compounds with chlorine or with chloride with the group 1 metals, as they get bigger, as you go down the column, our bonds are going to get longer, right? That's pretty predictable, right? Because the atoms are getting bigger. So we would predict that the lattice energy should get lower as you go down because the bonds are longer and therefore weaker. And that's exactly what we see. So we see that here's sodium chloride, the value that we calculated before. The value with the shorter bonded lithium is even higher. And with the longer bonded potassium chloride and cesium chloride, we get progressively lower lattice energies. So we can sum this up by saying the bigger the atoms, the longer the bonds are going to be, the weaker the bonds will be, the lower the lattice energy. Okay, so that's one trend we can look at for lattice energy. Now another one is going to be based on the magnitude of the charge. So remember, the two variables that we look at are distance apart and how big the charges are. So if we think about the size of the charges, right, it's going to affect how strong they're attracted. So the attractive forces between opposite charged particles is higher as the charges get bigger in magnitude. So in other words, the attraction between positive 2 ions, or between positive 2 and negative 2 ions, is going to be greater than the attraction between positive 1 and negative 1. Right? So the larger charge means that the ions are more strongly attracted. So larger charge equals stronger attraction. Stronger attraction equals larger lattice energy, right? Anything that makes the bond stronger is going to make it harder to break down. So if we look at these now, and we've selectively chose sets of ions here that have similar bond lengths. So we're not seeing the bond length trend that we saw in the previous slide. So we're isolating this trend to just simply how big the charges are. So we got about the same length, but we have bigger charges here. And if we look at our ionization, or we look at our lattice energies, we see that the calcium oxide lattice energy is much, much bigger than, say, the sodium fluoride lattice energy. You know, over 3 times as big. Now, what this tells me is if we look at this chart versus the other chart, where the difference was, you know, less than 100 kilojoules as we progressively got longer, you know, there's a huge difference here. And so of these two factors of magnitude of charge and distance of separation, the magnitude of charge is generally the more important one. It's going to make the bigger impact. And so again, larger charge equals stronger attraction, which equals bigger lattice energy. Okay. So now that we've sort of talked about this ionic bonding idea, and so these results, they allow us to make a few predictions. So based on the strength of the lattice energies, right, these large values of lattice energies, and the non-directional nature of an ionic bond, right, allows us to predict that ionic compounds should have pretty high melting points, meaning it's going to take a lot of energy to break down those ionic bonds and to transition from a solid metal into a liquid. Now, we don't have to totally break all of the lattice energy, but we have to break down some of these bonds, and that's still going to take quite a lot of energy. So we would predict high melting points and boiling points, if appropriate, for ionic compounds. And of course, the larger the lattice energy, the higher the melting point should be. So if we look at some of those values, we could predict that, for example, sodium chloride should have a higher melting point than lithium chloride because of the higher lattice energy. Or vice versa, should have a lower melting point because of the lower lattice energy. And indeed, in general, ionic compounds have very high melting points, well above 300 degrees typically. For example, sodium chloride, which we sort of used as our model, has about 800 degrees Celsius as its melting point, so quite high. And as a result, all ionic compounds are solids at room temperature, right? We don't have any liquid ionic compounds, at least at any kind of reasonable temperature, right? Especially, room temperature. So what else can tell? So it tells us we have high melting points. Now, another thing that these ideas can tell us is that ionic solids should not conduct electricity, right? Because the ions are fixed in place. And if the ions are fixed in place, then we don't have any way to move the electrons around, right? So the charges have to be mobile in order to conduct electricity. And so we would predict that the solid state should not conduct electricity, but the liquid state should conduct electricity. And this is indeed what we see, right? Solid sodium chloride, right? No conductivity. If we melt it, if we try to conduct through molten sodium chloride, it definitely conducts electricity, right? And this is indeed how we make a lot of sodium metal, is we take molten sodium chloride and we run electricity through it. We do what's called electrolysis. And this is something you look at in Chem 2, but this is a way that pure sodium metal is made, because remember, it can't be found in nature because it's too reactive. But in the liquid, the ions are mobile, which allows charge movement, which is what we need for conduction of electricity. This is also why we would predict that solutions of ionic compounds, so salt water, for example, would conduct electricity, because we know that when we dissolve ionic compounds, the lattice structure breaks down and we get free ions, and those ions are moving around in solution, and so the salt water becomes conductive. So while the solid ionic compound is non-conductive because the ions are fixed, both the liquid phase and the solution phase are conductive. And so these basic ideas that we have about ionic compounds, our bonding model, right, allows us to correctly predict, many of the basic properties of ionic compounds. So in the last couple slides, I simply want to